when we work with multisim, you use VCC as a power terminal, right? That give us 5 volts, and also we use ground. But for the CMOS, sometimes you will see VDD and VSS pins. So what is? So VDD LED or VDD pin is labeled, it means VCC as in TTL by manufacturer. So it just give us some positive terminal. So in the case of TTL, it will be 5 volts, but in the case of CMOS, it may be 3 volts, it may be 5 volts, it may be 10 volts, it may be 15 volts. So what is a D in VDD? Stands for the drain supply. So it's just, from the, it goes from the electronics, okay? So VSS LED or VSS pin of the CMOS unit is connected to the negative of the power supply, which is connected to the ground. So this connection is called GND in TTL by some manufacturers. Okay, so S is stands for the source supply. So just D means drain supplies and C means source supply. As I mentioned, you can see some volt range of the CMOS integrated circuits. Okay, now we switch to the other topics of today's lecture. It's interfacing. So we'll talk first about interfacing TTL and CMOS with switches. So actually, in multi-SIM, we always interface some switch. For example, we use SPDT switch, and we interface this switch with TTL or CMOS. But in the multi-SIM, there is no lot of differences. Yes, it's just simulation program. But when we work really with hardware, it's very important TTL or CMOS because it's real stuff. It's not simulation. So one of the most common means of entering information into digital system is the use of switches or keyboard, right? So for example, some digital clock, you can have some switches or keys on calculator or keyboard. Here we will detail several methods of using switch. Actually, it's easy, it's not so complicated. And here, some button switch to some simple TTL. So what here, our switch is input is wired to the ground. So actually when we push, when it's closed, input means 0, it means 1. But when it's opened, it will float because we'll not apply the high voltage. But in the simple TTL, when the input is float, it means it's high. So in the case of TTL, it works. Which will drop the input of the TTL inverter to ground level. I mentioned that. Releasing the push button, switch opens the switch. So it will be in this position when it is released. It's float. But in the simple TTL, it means it will has logic high level. So it is not necessary actually to connect to the high. If it will float, it means it will. So it's just designed such way. Okay. When we performed some lab works, actually we used active low switch interface, or we use active high switch interface. So let's consider some low. So what does it? So for example, let's consider this simple circuit. So we have this same TTL, and here actually we connected, we wired some pull-up resistor. Why? Because we do not want to when it's opened, we do not want that the input floating. We want that input was high, really high. So for this reason, we connect here this 10 kilo ohms resistor, and we call this pull-up resistor. Why pull-up? Because it will apply to this input when it's opened. It will apply to this input 5 volt. So it will be exactly 5 volts. When I push, current here potential will be 0. So actually when it's closed, we apply 0, low. When it's opened, we apply 5 volts. Why? Because this pull-up resistor give us here 5 volts. Here in the previous, you can see we don't have any pull-up resistor, it will float. Okay, so but we call this switch low switch. Why? Because you can see that it's called active low switches because the inputs go low. So these inputs go low only when the switch is activated. So when we activate this one, input will be low because it will be connected directly to the ground, right? So when switch is deactivated, when it's opened, this pull-up resistor gives 5 volts to the input. Okay, so I actually explained this. And next, let's consider the active high switch interface using pull-up down resistor, right? So this pull-up, this pull-down resistor. So actually, they look the same, but here you can see that when switch is deactivated, when it's opened, we connected through this pull-down resistor. We connected input to the ground. So my question for you, why here we use 330 ohm, but here we use 10,000 ohm? Can you have some idea? So if you will check the previous diagram, so because you should understand when our low is high, our input is low, it will take about 16 milliamperes, right? For this reason, we need to use resistance with relatively low resistance. But when input is high, and in this case, it will operate at the current about 400 micro. For this reason, we use this resistors with high values. Here we use this resistor with low value. So when we activated this switch, we apply to the input exactly 5 volts. For this reason, we call this active high switch interface. Okay, so next, so this was for TTL. It was for TTL inverter. But here let's consider switch to CMOS interfaces because of course inverter, it is inverter, right? So its job is to just convert, to complement, to invert the, for example, the output will be 0, input will be 0, output will be 1, and vice versa. Here is the same, but the interfacing can be different. And for example, here you can see that when we use CMOS inverter, to use active low switch interface, we need to use pull-up resistor, right? But here we use pull-up resistor not 10 kilo ohm, we use 100 kilo ohm. So why? Because you need to remember the input. We need to understand current drive, right? When the input is high, so it takes about 40 microamperes. For this reason, we use so high resistance here. So it's the same with these ones, but the difference only in the resistivity. So actually, you do not need to memorize this one because you actually can just calculate because you will have the tables, and from tables you can find the value of current, and you can just refer to the just to this diagram. But I want that you understand this, why we use here 100 and why we use, in this case, we use 10. Okay, so let's consider the active high. So it's the same as with TTL, but here we use pull down resistor, but the value is the same. Can you see? Because the current is current when it's low and current when it's high, input current is comparable. So is okay. So I mentioned this once. Next, actually we talked about switch debouncing and in the first, or maybe in the second lecture, and on the multi-slim you performed one lap when we constructed switch debouncing circuit. So what is the debouncing? When we switch your when you turn on or turn off your switch, because of this mechanical debouncing, yeah, we have some voltage debouncing. So it can generate some true, some false, some false high value or some false low value. For this reason, we need to use some switch debouncing. Previously, we considered the circuits, they was not debounced, right? For example, consider this circuit. Here we have some decade counter. So this counter can count up to how much? Up to 9, up to 10, right? So when you push button, it will count 1. You push second time, it will count 2. It says up to 9. Then when you push again, it should show us 10, but it doesn't show. It's come back to the 0. So, but this switch is not debounced, and when you push, it can be some spikes in the here in the circuit, and for this reason we can have some false high input, and it will not work properly. So for this reason we need to design some switch debouncing. So tomorrow on lab, I don't remember, but there is one, I think, lab where you need to do this kind of switch debouncing circuit again. So here you can see we use 2 NAND gates, and just by connecting like this, you can get simple switch debouncing circuit. And when we switch your turn on and turn off your switch, so it will properly count each input. So adding the bouncing circuit to make the decimal counter work properly. Okay, so here we can see that cross-coupled NAND gates. Why cross-coupled? Because we connect input of one NAND to the output of other. Okay, next. Here you can see other type of switch debouncing circuits, but it's simple one. Here just pull-up resistor is connected and some capacitance. So, but this one will work not for all the integrated circuit. It can work for this type of. Okay, let's consider other one. It's similar to the first one, but you can see here we have some resistors. So it actually depends what kind of integrated circuit you're using. Here you can see that this one is work for this CMOS with 4000 series, right? Here, this debouncing switch can be wired to also to the 4000 series, but also to the 74HA00 series, and also to the TTL 7400 and some FACT series CMOS. Next one, other switch debouncing circuits. It's not so different by the previous ones, but you can see also. So, in this one, have you seen it before, this circuit? Guys? Have you seen this before?
Yeah, it was about delaying the
Yes.
like
Yes, we actually simulated this on the multi-slim, right? So here we use this timer integrated circuit 555. So it was in the first lab. So actually, how it works, when you push, it's here, right? So your output. So when it's closed, so it's high. Then here we open. And it should go load, right? But for some reason it doesn't go. It will not load. It will continue to high, and we have some delay. Then it will go to low value. So actually this delay we can adjust by adjusting this capacitance C2 or this resistance. So actually you tried on the multi-slim and you saw on the oscilloscope that actually you can change this delay time. So interfacing TTL and CMOS with LIGs. Okay, so now we interfaced our integrated circuit with switch, because switch it is not necessary switch, because it may be some keyboard like, yes, because switch keyboards, it's the tools by which we give some inputs, some information to our circuit, right? But we need also some output, and one of the simple outputs from the integrated circuits, it's some kind of indicator, and it is LID, right? And we already in our lab work, when we assemble some integrated circuit, we'll check how it's work by connecting it to the LID. If our LID lights, it means that we have signal. If it does not light, we don't have signal. So, but maybe it seems easy, but actually you need to understand, you need to able to properly connect LID to integrated circuit. So let's consider some simple interfacing LID with TTL and CMOS integrated circuit. So actually LID can work at the volt 2 volt, so it's consume about 20 to 30 milliamperes, right? So actually, but you can connect 1.7 and or to 1.8 and also will work, but your intensity of the light will not be too. It will be it will light dimly. Dimly it means it не ярко, да? Okay, so let's consider some LED interfacing to CMOS inverter. So here we have inverter. So CMOS active high. So high output will be low, right? It means that LED will not light. Why? Because here should be high. So when our output will be low, here will be high, and in this case it will light. So it's actually it's simple, and you can see that we do not need, when we use some CMOS, for example, this simple CMOS, we do not need to connect some series resistors. It can work because the current will not be too high, so it's okay. This is CMOS active low, CMOS active high, active low. Why? Because the output, when output will be low, then current will go through the LED and it will light. So what difference? Here you wire the anode. This part of the LED we call anode. We connect anode to the output of the our inverter. Here this part we call cathode, and we wire the cathode to the output. Okay, next CMOS to LED interfacing. So here what difference? So here actually when it's 5 volt, you do not need to use series resistance. When your CMOS operate on 5 volts, you do not need to use series resistance. But here you can see when it's operate in the range of 10-15 volts, fire your LED. For this reason, you need to connect some limiting resistor. We call this limiting. Why? Because it's limit current through the LED. So it's actually the same to this one. Yes, so it's CMOS active high, but with the LED. It is CMOS active low with resistance. So it's the same. But your CMOS working at other voltage, it's higher voltage. For this reason, you need to connect limiting resistance in order to limit current through LED. Okay, so I think it's clear. Next on CMOS to LED. So here's the difference? Here, for example, can be some buffer, right? Here we use just inverter, but this is a buffer. So what difference between inverter and buffer? it is inverting buffer. So buffer is just, it's similar to inverter, but you know, driving capability of buffer is greater. So buffer actually can give us a lot of more current in comparison with the inverter. So when we connect them to the CMOS buffer, you also need to use this limiting resistor. So here the same, but you connect cathode. But here it's inverting buffer. It is not inverting buffer. What next? I think here all of this is clear. So TTL to LED interfacing. So actually, in our multi-slim works, we usually do this kind of experiment, right? So we use some, actually we type 7400 inverter, we use 7404 inverter, we use in multi-slim, and you see when we do not use this resistance, your LED will, you can actually break your LED. For this reason, we need to use this series resistance. But you can see here, series resistance is different, right? This limiting resistance. Why? Because we could not use 1 kilo ohm. Why? Because the current that give this TTL is different that current give us the CMOS. For this reason, you can connect the TTL standard inverter to LED by using 150 resistor with the value 150 ohms. So it's a TTL active high, and here you can see TTL active low. So the same, but you connect cathode to the inverter and the anode to the VCC, right? Next, at the beginning I mentioned that for example, current sourcing and current sinking. Sometimes it's difficult to pronounce. Not thinking, not sinking. For us, for not native, it's really difficult. But sometimes you can understand from the meaning, right? Current thinking. Okay. Думать, да? Current sourcing. So what is the current sourcing? Here you can see what is this logic. What kind of logic gate is this one? Yes, it's AND, right? So you can see that we wired LED, we wired anode of the LED to the output of the AND gates. So, and the cathode we wired to the ground. So you should know from the physics that conventional current goes from the positive to the negative, right? So when the input to the AND gate high, it means here also will be high. So approximately, it will not be 5 volt. You saw it will be maybe 3.5, maybe it will be 3 volts. So it depends on the TTL. So and current will go from the, actually we take current from the AND gates, from the integrated circuit, and it goes through the LED. So for this reason, current sourcing, we name it current sourcing. For example, here, connection is different, right? So we actually cathode to the, it's NAND, it's not AND, it's NAND. And you can see that anode we connected to the VCC. So here when the input of the NAND high, here will be output is low, right? It means current will go from the internal, from this power supply, through the limiting resistance LED. It will think, right? It will go to the NAND gate and then to the ground. So we say this current thinking. So I guess now you understand what means current sourcing when we give current from integrated circuit to output device. In this case, output device is LED, right? And current sinking, when we when our output device gives the current to our gates, to our gate. Okay, so before we consider just interfacing LED with the integrated circuit, but we can actually improve this connection by using some transistor. So you can see this some NPN transistors. So how it works? Well, for example, to understand this, you should understand that current go from this 5 volts through this limiting resistors, through this LED, to the collector and to the emitter. So current here can go from this 5 volt terminals to the ground. But this resistor, we can control its resistance. So when we apply here, when this input will be high, current can go. When the input will be low, current cannot go. So you can see when your input will be 0, your output will be high. It means that here will be, we call this base. It's collector, it's emitter. Base will be high, and the current can go through this transistor, through the system, and actually our LED will light. So why we use here the transistor? First of all, we use transistor when we don't want that current will go through our integrated circuit. So here you can see some high resistance, and it means that there will not be too much current through this resistor. It's first, and second, for example, it may be not LED, it may be other some kind of output device, and it can take a lot of current, and we do not want that too much current will go through our integrated circuit. For this reason, we can use this transistor, and all of the current will go on through the transistor. Oh, what difference here? It's other type of, so it's NPN transistor, it's PNP transistor. So what NPN? NPN means n-doped. So it's just physics. We do not want to go into the details. This is PNP transistor driver. So how it works actually? So when here input will be low, current will go through. If input will be high, current cannot go through. So that's the difference between here NPN and PNP. So here is interesting circuit. So we can use it as some logic probe. For example, you can connect this to some point in your circuit, and if it will be high, what do you think? This resistor will light or this resistor will light? Its input will be high. What do you think? So we have LED 1, LED 2. My question for you: if input will be high, what's of this LED will light? Is there any idea? So when this input will be high, it means this input will be low. It means that here it is NPN. It will be low, so current cannot go through. But here also will be low. It means that current can go. So this LED, when input is high, this LED will light, and we'll understand it. If when it's green, we understand that our input are high. But when it's low, it means that this will output will be here high. It will be high and current goes through. This also will be high, but current cannot go through this transistor. So red LED will light. It means that input is low. So it's some logic, simplified logic probes that you can do yourself, and in the future you can if you will work in some computer network system, you can check just is there a signal or not by using this kind of simple logic probe. Okay, let's consider interfacing TTL and CMOS integrated circuit. Sometimes we need to interface TTL with CMOS or CMOS with TTL. So actually, we could not do it directly. Why? Because you can see current is different, voltage is different, right? So actually here, if we take only low, here when you connect input of some CMOS to the output of some TTL, when we have low, I think it will work fine. Why? Because it means 0.8, right? Here it is within this range, so it is fine. But when your output of the standard TTL will be high, so you can see that it will be undefined region. So actually, for this reason, we need to use some interfacing. So how can we do it? It's simple. We can use, pull-up resistor, for example. Consider this circuit. So here we connect TTL inverter to CMOS inverter, right? And here we use pull-up resistor. Why? Because when it's low, it's fine. So we can apply low to this low from TTL output to the input of CMOS. Because if you consider, its value is within this range. But when you apply high, so it will be input can be in undefined region. For this reason, we connect here pull-up resistor that connected wire to the VCC to 5 volts. So this pull-up resistor, here will be high. For example, this input will be 3.5, but this pull-up resistor will pull up its value up to 5 volts. So this interfacing will work properly. Okay. Next, interfacing TTL and CMOS. Let's continue. So what here? So interfacing TTL and CMOS when both use a common 5 volt power supply. So here we'll considering just some simple interfacing when both TTL and CMOS using the same power supply, 5 volts, right? So let's consider this one. Here, low power Schottky TTL to CMOS interfacing using a pull-up resistor. So to connect low power Schottky TTL, we also need to use pull-up resistor. Here you can see in this example it will be 2.2 kilo ohm. So here what's the difference? So this CMOS to low power Schottky TTL interfacing. But when we'll connect CMOS to low power Schottky TTL, so here you can see we do not need to use the pull-up resistor. Why? Because the voltage range is comparable. For this reason, here you do not need to use the pull-up resistor. But it is not, common case. Sometimes it is such simple, but mostly it's more complicated. Is driving an LCD TTL inverter directly in this example, right? But sometimes, however, most CMOS cannot drive standard TTL inputs without special interfacing, so we need to come up with special interfacing. Next, here we considered using pull-up resistors, but manufacturers of integrated circuit have made interfacing easier. How? They just, design some special buffers. Designers and who design some circuits, they can use these buffers. Here's some examples. Interface to the standard TTL by using some CMOS buffer. So if you connect the output of this CMOS to the input of this CMOS buffer and the output of this CMOS buffer to the input, so all of these are connected to the same power supply, so this circuit will work properly. So in this case, you do not need to use pull-up resistor, you can use some buffer. Special buffer, this buffer designed specifically for interfacing CMOS to standard TTL. Okay, so next, the problem voltage. Okay, so sometimes this voltage incompatibility from TTL to CMOS was solved by using a pull-up resistor, right? And we all see that. But there is other method, and here, for example, you can use specially designed integrated circuit. So it's like inverter. It's not inverter, it's like buffer, right? So this will, so you can connect and integrate circuit. Okay. His other can be directly connected to any TTL. There's no need any interfacing. It will work. Why? Because voltage will be comparable and currents will be fine, but it's not always work. Here we'll have some other. You can, you will read, of course, this on the book, on the chapter 5. Here you can see we can use some pull-up resistors, but I want that you understand what does a T means. So sometimes in CMOS we will have on the label some T. So this CMOS with label T specifically designed in order to directly be connected to the TTL, or this TMOS, this CMOS with label T, they can, replace TTL. So for this reason, this type of CMOS was designed. So you can see that here interfacing, simply the interfacing without any pull-up resistor or buffers, etc. Next, so this is different. Why? Because sometimes we need to use a different power supply voltage. So consider this circuit. So here our TTL inverter, and we need to connect it to the CMOS inverter, but this TTL works at the power supply 5 volts, this at power supply 10. So you could not directly connect. So for this reason, you can use the in-pen transistor. So it's very simple techniques. Okay, so let's consider other type. So instead of transistor, you can use special buffer. Connect the TTL that works at voltage 5 volts to the inverter that works at the voltage 10 volts. So you need to use this special buffer. It must be 7406 or 7416, and also you need to use some pull-up resistor here. Of course, guys, you do not need to memorize this whole. It will not be asked on the test. You just should understand that there is some interfacing problem, and it can be solved by using transistor or special design buffer and other circuits. So here, what this I think it's here you need to connect to the TTL that works at power supply 5 volts, and for this reason you can use this CMOS buffer 4049, right? And this kind of circuit you can use. So, okay, so for now we considered interfacing of integrated circuit with switch with. Can you see me? I think you could not see me, right? I need to. Now, can you see me, right?
Yes.
Okay, so for now, we considered interfacing integrated circuit with switch, with LID, and integrated circuit, which is other, and about interfacing with output devices, because it's I think it's a goal of any why we're designing some circuit because we want that this circuit performs some function, right? So for example, you can drive some motors, you can drive, I don't know, a lot of things. And the objective of many, for example, Arduino, you know, microcontrollers, you can buy do some simple robots or some kind of interesting projects. And so when you design these digital systems, you need to connect your circuit to the output device. And the output device can be some electromechanical device. So what kind of device? So output device, let's consider, for example, LED, but of course LED it is not electromechanical. Buzzer. So for example, buzzer, right? So buzzer is just simple. How can I? Next, relay. So relay, it's also very important elements because through a relay you can or circuit to the circuits that will consume a lot of current. For example, through a relay you can connect your circuit and control your, for example, you can control some motors or some solenoids. So for this reason you need to know how to connect your circuit to the relay and from the relay to some output devices. For example, output device can be electric motor, it can be stepper motor, it can be solenoid. So all of this we call electromechanical system: buzzer, relay, electric motor, solenoid, stepper. Sorry. How much time we have? How much time we have? 4 minutes? 5 minutes?
Yes.
Yes.
Okay, so let's go faster. Interfacing with buzzers. So it's not difficult, guys, and on the lab work you will try, because on the multi-slim there is some buzzer, and you can try doing this kind of simple interfacing. But here, for example, you use the inverter, and when you apply where your input will be high, here will be low, and current can go through the buzzer, so it will be synced to the integrated circuit, and this buzzer will work, give some sound. So, but you need to pay attention. Here we connected. Here it is it is a diode. It is not LED. It is not light emitting diode. It's just simple diode. So this diode is connected. So why it's connected? Difficult to explain, by one sentence. But you should understand that it just protects your circuit, this part, from some, undesired. The diode across the buzzer is to suppress any transient voltage that might be induced in the system by the buzzers. So sometimes when we not needed voltage spike, then can reason we connect this transient voltages, but do not think about this, but just pay attention why we connected this diode. So actually this is the same one as this one, but we connected through the transistor, right? NPN transistor. So like this, but through the transistor. Interfacing using relays. So we interface some inverter, TTL or fact inverter, through the resistor. We interface to the relay. So this relay actually then we can connect this relays to some output device and control. We can, just clicking on the mouse in your computer, you can just switch this TTL if you computer, and you can control some let me show you here. Here's the some diagram. How can we connect motor through relay? So relay protect your circuit from high current, because DC motor can consume a lot of current. So it's high voltage, but your circuit is working on the low voltage, for example, 5 volts. Here, example, you can connect to the solenoid. So what difference between the motors and solenoid? So motors is just rotate, yes. Solenoid, it moves up or down. Guys, okay, we don't have time, but you need to read optoisolators on the chapter 5. So have 1 minute. So it will be your homework to finish the slides. I will upload on the Moodle, and you need to read chapter 5. Okay, guys, do you have any question about this today's? Let's do some summary. So today we learned about some important parameters for integrated circuit. It is voltage profiles, noise margin, propagation delay, power dissipation. Next, we consider interfacing with switch, interfacing with LED, interfacing between two families of integrated circuit, interfacing with with some electromechanical devices, and you need to read other interfacing in chapter 5, because we have only 10 weeks and we don't have a lot of time to cover all of the topics from the book, but you can read yourself. So do you have questions, guys?
No.
So in this case, we don't have questions. Tomorrow will be lab work, so please come and accomplish your 5. Who did not do other, you need to finish. Hurry up. So I will upload these slides. I will upload homework, and but concentrate on the reading. If you will read, you can pass test, and you can easily do the lab work. Okay, in this case, thank you for that you were today in lecture. So see you tomorrow. Bye all.
Thanks for listening.
Mm-hmm.
Bye-bye.